This video presents Poisson's equation and Laplace's equation for electrostatic fields. Okay, so here's an example of a problem that we would like to solve. We have a volumetric charge density contained within a volume V, and the volumetric charge density is rho sub V as usual. And at some point P, we are interested in finding some field quantity, such as the voltage at point P or the electric field at point P. So from what we've just seen, we know that Laplace's equation applies, and if we can solve this equation, given this volumetric charge density, rho sub V, we can find V, and from V we know that we can then find E by going backwards. So this is a challenging problem to solve, or more challenging to solve, because it is again a non-homogeneous differential equation. And it would be easier to solve if the right-hand side were 0. In fact, the right-hand side is 0 in many parts of this problem. If I take this field point, or this observation point, and I move it outside V, so let's say I move it outside of this volume to this point shown here, then actually at that point, there is no volumetric charge density. So the right-hand side is 0, and we get the homogeneous equation that we're looking for. So that equation, where the right-hand side is 0, is called Laplace's equation. So it is a special case of Poisson's equation, and it holds everywhere outside the source region. So everywhere outside this volume V, our problem reduces to solving this homogeneous differential equation, and it basically turns into a boundary value problem. It's important to also realize that we can apply the same concept to many other charge distributions, not just volumetric charge distributions. So the same is true in turning Poisson's equation into Laplace's equation if we had a surface charge density, or a line charge density, or even a discrete distribution of point charges, so long as our observation is not coincident with the charge density itself or the point charges in the case of a discrete distribution, we can turn the problem into solving Laplace's equation. And even with a combination of volumetric, surface, line, and discrete charge distributions, we can apply the same concept.
basically. So if you forget everything else I say tonight, the one thing to remember here is that Earth's atmosphere is always electrified. Normally, we just think about charge when there's thunderstorms and lightning around, but it's electrified all the time, and charge is continuously generated. And that's through a process called ionization. So positive and negative charge is created by ionization all the time. And in our atmosphere, there are two sources of ionization. The first is from galactic cosmic rays. So these are highly energetic particles from basically outer space, from outside our solar system, and they enter Earth's atmosphere from above. And as they do so, they create a cascade of charged particles right down to the surface. And because they come from outside our solar system, they're modulated by solar activity. So they respond to magnetic fields. The other source of ionization is radioactivity at the Earth's surface. So this is mostly from gamma radiation from the soil. And so this emits ions which can be transported upwards, but they're typically trapped in the boundary layer. So they're stuck in the lowest kilometer of the atmosphere. We're looking at this. So how do these clouds become charged? Well, to do that, we have to think about some of these atmospheric electricity parameters a bit more. So we have to consider what's called conductivity. So conductivity is the ability of the air for a current to flow in the air. And it depends on this ionization from our cosmic rays and from our radioactivity. So these tiny little ions that are created in a cloud, they become attached to the droplets. And that means that the conductivity goes down when you have a cloud layer. So this is our cloud layer. We're going up through a cloud layer. So our conductivity decreases, is low in the cloud, and it increases when we get above the cloud. If we go to Ohm's law, which if you remember back to your school days, you probably did this in the form of V equals IR. It's basically the same equation, just written in a different way. And that says if you have a current, so in this case, JC, it's flowing through the cloud, and you have a conductivity or resistance, basically the same, the inverse, then if you have an electric field, then the conductivity and the electric field are inversely related if the current stays the same. So because we have a conductivity decrease, we must have an electric field increase in the cloud. And if we take another relatively simple law of electrostatics, so Poisson's equation, that says if you have a gradient in electric field, then you will create a charge, a space charge, rho. So you see that there's a gradient in the electric field on the bottom edge of the cloud and on the top edge of the cloud. So that means that we should get a charge, rho. And that's what we see here. So this is our charge density. So because of the direction of the field and the current flow, we should get negative charge at the base of the cloud and positive charge at the top. And if we manipulate these equations a little bit more, this charge depends on a few things. It depends on the conduction current, so our JC, which depends on the global circuit and therefore the thunderstorms. It depends on the conductivity, which depends on the ionization from the cosmic rays. It depends on the gradient of the conductivity, which is this bit here, which depends on the height of the cloud, but also the cloud droplet properties. So if we have a really sharp cloud edge, we should see more charge than if we have a woolly one, if you like. So that's what theory predicts. So our theory predicts that cloud edges are charged and that the charge should be transferred to the cloud droplets. So what does this charging of droplets do? Well, we'll discuss this in a bit more detail shortly, but basically it affects the microphysical interactions between aerosol particles and droplets. And collisions and coalescence, which is something that's particularly important in clouds, is affected by charge. So this means that things like the lifetime of the droplets, how long they last, and how they grow can be affected by charge. And many of you will know that it's these small-scale cloud microphysical processes that determine the large-scale properties of the cloud, such as the height of the cloud, its opacity, or how much its reflectivity, basically, how long the cloud lasts, and even the rainfall.
It's called the ambipolar field, and it's an agent of chaos. It's an electrical field. It begins at about 250 kilometers above your head, and it keeps going. The atmosphere up there is different than the atmosphere down here. Thinner, right? There's less of it. So think about just one atom. Here it is. The sun shines on it, it breaks off this electron. So now we have this negatively charged electron and this positively charged ion, and the two are attracted towards each other. The electron would happily escape all by itself, but the ion still feels the big tug of gravity. So as the electron tries to pull away, the electric force forms between the two to restrain it, to keep it from escaping. And it also helps pull the ion upwards. The field works in both directions. It is ambipolar. Imagine you're walking a dog, and you've got a tiny, tiny little dog, and it's pulling on a leash. That dog's going nowhere. This ion and electron pair that you've been thinking about, they're only one in an enormous sea of the ionosphere. But overall, because gravity's pulling down on the ions, it adds up. And over a large distance, you get this field forming. It's like this conveyor belt that's countering gravity and lifting the ions up so they can escape to space, which is why it may have had an impact on the evolution of the atmosphere. 3, 2, 1, hit down! Let it go! During the 15-minute suborbital flight, we successfully measured this ambipolar field for the first time. When you add up all of the strength of it over the whole flight, the whole potential drop was only about half a volt. And that's nothing, right? That's about as strong as one of those tiny little watch batteries. But that's exactly the amount that you need to explain this, polar wind escape, this outflow. Because we measured it for the first time, we can actually understand the role it plays in the atmosphere. And despite being weak, it's incredibly important. It counters gravity and it basically lifts the skies up. It's like this conveyor belt that's lifting this atmosphere up into space.